Now let's discuss the natural response of RC circuits. So we talk about the natural or transient response, which we'll also see it called. We're referring to the response of the circuit when stored energy in a capacitor is released into the rest of the circuit after a switching event takes place. So we're going to have something we're going to call a switching event. We're going to change the topology of a circuit. We're going to have a capacitor that's had some kind of initial condition established in it where it has energy stored in it. And then as a result of that, we're going to put that energy, release it back into the circuit. So the question is what kind of voltages and currents do we get out of that? Well, the basic concept behind the type of response we're going to do really comes down to understanding Thevenin and Norton's theorem. So what we're going to see is this. A first order RC circuit can always be reduced to one of two topologies. So I can either turn it into this, a Thevenin voltage and Thevenin resistance connected across a capacitor, or I can transform any circuit into this. A Norton equivalent circuit. Connected across a capacitor. So it doesn't matter what circuit I start with. If it has a capacitor in it and it's composed of other circuit elements, I can always take those other circuit elements and reduce them down to either a Thevenin or a Norton equivalent circuit. Which means that once I do that transformation, no matter what kind of circuit I start with, I can use the same math to describe every circuit. So let's consider the following example of a way of doing this. Let's look at this. Let's assume you had a circuit like this. Now in this circuit, I'm going to include something you're going to be seeing a great deal of, and that is a switch. What I have is a switch that can flip from this position over to that position, and in this case, I'm going to say this switching event is going to occur at time t equals 0. I'll call that resistor R. So here we have a circuit kind of distilled down to the basics here. Now what's happening here is, first of all, my source VO is going to establish an initial condition in that capacitor before the switching event. So the source creates the initial condition. Energy is stored in that capacitor. And then at time t equals 0, I'm going to remove the effect of that source. I'm going to disconnect that capacitor so that it no longer can be affected by it. So the source is effectively removed. So in some circuits, you're going to see that we use switches. In other circuits, later on, I'm going to show you how to mathematically describe a source which goes to a 0 value. It actually changes its value. But regardless, the idea is the same. We're going to remove the influence of that source at some switching event or some topological change that's going to happen at t equals 0. Now, I want to emphasize, I could make my switching event happen at any time. The math would be essentially the same. The difference is by using t equals 0, I am making my numbers a little bit easier to handle. So this could be any arbitrary time when the switching event occurs, but we are going to, just about every case, we're going to use t equals 0 as we go through this material, just because that makes things a little bit simpler for us. All right? So we're going to start by assuming that prior to the switching event, for t less than 0, we're going to assume this circuit is in what's called a steady state condition. So what does steady state mean? Steady state means nothing's changing in the circuit. So it means, in other words, that di dt and dv dt are equal to 0 throughout the entire circuit. You'll see this used over and over again as we go through these materials, through these problems, the idea of steady state. So, in other words, this circuit's been sitting this way in this particular topology for a very, very long time. And all the transient events have long since died out. So everything is, in effect, acting like a DC circuit. Nothing's changing. All right? Well, in this case, if that is true, I'm going to define a voltage VC across this capacitor. And what I'm going to do is, if I'm in steady state for t less than 0, I know that the current through the capacitor, IC, must be equal to 0. So once again, this is a consequence of the capacitor's behavior. I is equal to C dV dt. If nothing's changing, the current must be equal to 0. So in this case, since the current through the capacitor is the same current flowing around this loop, that means that I have 0 amps flowing through this resistor. So in other words, I've got 0 volts across that resistor R sub O. And if that's the case, then I can write myself a little KVL equation. By KVL, VO is equal to 0 plus VC. Therefore, VC is equal to VO. So the voltage across the capacitor is equal to the voltage VO in steady state operation. All right? This is the initial condition for the capacitor. All right, so we're in this condition for time t less than 0. Then at time t equals 0, the circuit's going to switch. Now, just want to point out, for time t less than 0, there was no current flowing through that resistor because clearly this was disconnected on one end. So that resistor was just doing nothing. It was hanging off and nothing was happening. All the action was over here. This is where I had the complete loop. So now for t equals 0, this is going to switch over, and now we're going to have this. So for t greater than or equal to 0, the switch flips over. Okay, now what happens? Okay, so I'm going to go ahead, I'm going to start treating this nodally. I'm going to ground this bottom node here. So I've switched over at t equals 0, and notice now I've got a loop here connected, but note over here, this source and this resistor are now disconnected from that circuit. If you look at it, that current's got to be equal to 0 by inspection. And since we're only connected here on the ground node, there's no way that the voltage here at V0 can have any effect on those two elements over here. So what we've done here is I've gone through and these have effectively been removed from the circuit. These two elements will have no further effect on C. So there's no way that current or charge can move from the source into that capacitor. There's no connection. There's no path. All right? Which means the only thing left I have now is this loop over here. Let's go through and let's write ourselves a little KCL equation for this. So I'm going to call this node A, and I'm going to, now note I've still got the voltage VC for this capacitor. The voltage VC, since these two elements are now in parallel, must also be the voltage across the resistor. So I'm also going to define a current IR. And so in this case, what I'm going to have is that IC plus IR are equal to 0 by KCL. So that's for my node A. And therefore, C dVC dt, which is the current through the capacitor, plus VC over R, since the voltage across the capacitor must also be the voltage across the resistor. These must be equal to 0. Okay, I now have an equation that describes what's going to happen in this circuit for t greater than 0. And notice, this is a first-order differential equation. Okay. Now here's the nice thing about this. I'm going to go and solve this first-order differential equation. But once we get the solution, that solution is going to apply to every other circuit we can come up with in which we can take the capacitor and basically reduce the rest of the circuit to a single resistor. So I only need to do this once. After that, the same solution works for every first-order circuit. So let's do that. Let's rearrange a few terms here. So dVc dt should be equal to minus 1 over RC times Vc. Just rearranged a few terms here. Now let's bring all the Vc's and dVc's over to one side. So dVc over Vc will be equal to minus 1 over RC dt. So just rearranged a few terms to go from here to here. Now let's take this and we're going to integrate both sides of this. So let's do that. I'm going to use variables of integration and redefine this. So I'm going to be integrating from Vc at t0 to Vc at t of dx over x, and that'll be equal to minus, well, the minus 1 over RC is a constant. I'm just going to factor that out. So that's minus 1 over RC, integral from t0 to t of d tau. So in this case, x and tau are my variables of integration. And so from here, I can now go and evaluate these integrals. And what I'll get is the following. In this case, dx over x, when integrated, becomes the natural log of x. And we're going to evaluate that from Vc t0 to Vc of t. And that'll be equal to minus 1 over Rc of d tau when integrated just becomes tau, and that's going to be evaluated from t0 to t. So I'm going to evaluate those limits, and what I will get is that the natural log of Vc of t minus the natural log of Vc t0 will be equal to minus 1 over Rc t minus t0. Now at this point, t0 was the starting time for my integration, but as we've already said, these switching events are going to take place at time t equals 0 to make our math easier. So in this case, since t0 is equal to 0, then, in other words, that's when the switching event occurs. Then in this case, the natural log of Vct minus the natural log of Vc at 0 is equal to minus 1 over Rc times t. And now we're going to use a little bit of math here, rules of logs. The difference between two logs is the same as the log of the ratio of those two. So I can rewrite this and say that this is equal to the natural log of Vc t divided by Vc at 0. And that will be equal to minus 1 over Rc times t. And at this point, I'm going to raise both sides of this equation to e, the exponential power. When I do that, exponential natural log, those will cancel each other out. And what I'll wind up with then is the following. That VC of t divided by VC of 0 is equal to e to the minus 1 over RC times t. And now in this case I can multiply both sides times VC of 0, and therefore VC of t is just equal to VC of 0 e to the minus 1 over RC times t. So this will be the voltage across the capacitor, and of course also across the resistor, will be equal to VC0 times e to the minus 1 over RC times t for t greater than or equal to 0. Okay. Now, question, what is VC of 0? What is the voltage across the capacitor at time t equals 0? Okay, here is where something I mentioned to you in a previous lecture talked about the fact that capacitors have a certain property. We recall the voltage across a capacitor cannot change instantaneously. And remember, we mentioned this. I is equal to C dV dt. If we could change the voltage instantaneously across a capacitor, then dV dt would be infinite, and therefore we'd have infinite current. And physically that can't happen. So because of this, that means that the voltage across this capacitor doesn't change from the time just before to just after the switching event. So in other words, VC at 0 epsilon minus just before the switching event has to be equal to VC 0 plus just after the switching event. So if I basically reduce this to an infinitesimally small amount of time just before and just after the switching event, those voltages will be the same. And if that's true, that means that's equal to VC0. And recall that VC for t less than 0, as we calculated earlier for this circuit, is equal to V0. It's equal to the initial condition that we established in the capacitor. Therefore, VC of t will be equal to V sub O times e to the minus t divided by RC volts for t greater than or equal to 0. That's our result. That is the response, the voltage of the capacitor for t greater than or equal to 0. All right? Now, what does this look like? What kind of response is this? Let's plot this response out. If I were to plot VC as a function of time, prior to the switching event, VC is equal to 0. After the switching event, VC is equal to V0 times e to the minus t over RC. Well, when t is equal to 0, e to the minus 0 is just 1. So right at t equals 0, we still have the value equal to V0, but then as t gets larger, what we're going to have is exponential decay. So as t goes to infinity, Vc of t will go to 0 as t goes to infinity, and this will decay down to 0. All right? Now, something I'd like to point out to everybody, exponential responses are universal throughout nature. We are looking at the exponential response of a circuit as a capacitor discharges. You will find exponential responses all throughout engineering, both in nature as well as technology. So for example, if you are giving a patient a steady supply of a drug and then you remove that drug, what happens to the concentration of the drug in that patient's bloodstream? How can you describe that mathematically? Well, as it turns out, exponentially. If you are a mechanical engineer and you have a piece of metal that you have heated at a certain temperature, and then you move it to a cooler temperature and measure what happens to the temperature over time, how does it cool off? Exponential decay. So exponential response is universal. In other words, this kind of first order response is not limited to engineering, electrical engineering, or electronics. It is everywhere in nature. So when you're studying linear systems and studying first order responses, you're studying something that you can find basically throughout the universe in terms of that kind of phenomenon. Okay, so this is our very first equation, and once again note, as long as I can distill my circuit down to a single resistor and a single capacitor, and I know what the initial condition is, this solution works for every possible circuit you can come up with. So next time we're going to look at a consequence of this equation, and it has to do with this exponential decay. We're going to look at something called the time constant.